The last lecture that I'll give, and it's picking up on what we did this morning, which is to say, thinking about degradation mechanisms, and in this case, in particular, what happens with thermal effects in supercapacitors. I'll talk a little bit about batteries as well. But since this is my last lecture, I wanted to say thank you, certainly to the audience, to Professor Ritu Gupta, who organized this, and also going back in time. I actually have been coming to India for many years now, starting in the early 2000s, and then I did sabbatical leave in Bangalore, where I spent time with Professor C.N.R. Rao and Professor Kulkarni, and so they are wonderful friends of mine and mentors in many ways. And they've always been so hospitable to me. So I thank them. Also, much of the work that I'll talk about in this lecture comes from two people. Goping Xiong is shown in the top right, and Arpan Kundu sitting in front of a sculpture in Chicago. And so they did a lot of the work that I'll describe today. And then also my friends at JNCASR, where I spend a lot of my time down in Bangalore when I'm in India. Okay, so to some extent, what I will try to do is to sort of wrap up a number of different concepts that we've gone over. I hope that at this point in time, the chart here is somewhat familiar to you, in the sense that we're looking for, in an energy storage medium, we want high energy so that it will last a long time, and high power so that we could maybe put it into a circuit that has high-powered draw, some high-powered motor, or so that we could charge it faster, right? That's probably the more important thing to many of us. And right now, neither supercapacitors or batteries satisfy both of those. I think the desired place would be kind of above batteries in power so that we could charge them faster, but having the same amount of energy density. If we put that into a slightly different context with some more technologies listed here, you can see that gasoline engines and gas turbines have very high energy density, that's the specific energy, and high power. So really what we want, in a way, is we want to have an electrochemical system that acts a lot like an internal combustion system that you have in an automobile. But we don't want to have to burn fossil fuels in order to do that, right? So we'd like to be able to say, place a battery, pull power from solar panels into a battery, and then have that battery provide the kind of power and energy that an internal combustion engine can provide. So the main topic of this lecture is going to be on thermal effects in batteries and supercapacitors. So this is a reminder that electrochemical systems are highly thermally sensitive in general. And we'll talk about how that is and why. This is a picture of a Boeing Dreamliner after one of the batteries or something near the battery had caught on fire. And this was from the Dreamliner airplane, which just came out right after billions and billions of dollars were expended to develop this mostly composite aircraft, right? There was much press and hoopla around the launch of this new aircraft, and then in the first month, several fires happened on board, and that was a big problem, obviously from a PR standpoint, but from a technical standpoint, you can't not have an airplane catching fire, right? It just is a safety issue. Fortunately, these fires were happening on the ground, and they've since corrected it, but it's certainly a reminder that that heat and thermal energy is important to understand and control in these applications. The capacitor structure, I'm just putting this up here to remind you, they actually can come in many different forms, and they've evolved a long way past the original parallel plate capacitor, which is shown schematically on the left, into these roll formats. But when you start to roll an electrochemical system together, then you run the risk of thermally insulating it, right? So then the cooling that you would want to do for this device is more difficult because you can't reach the places where the heat is being generated, at least all of those places, easily, because generally these materials are thermally insulating. We'll talk a little bit about that. So then, just to remind you about the charging mechanisms in supercapacitors, I don't want you to forget this. You have the double layer effect. You have the Faradaic or pseudocapacitive effect. I hope that you appreciate all of the wonderful materials questions that go with that, right? So there are important materials questions at every level of a supercapacitor device, and I think it's important for you to appreciate all of them. And we'll touch on some of those a little bit later in this talk. So I'm going to move on to general thermal effects. And I would mention that even with supercapacitors, we've continued to say that supercapacitors tend to have better thermal behavior than batteries do. But even supercapacitors can burn out. Here's an example of something that was overcharged. Too much power was put into the device, and it couldn't handle it. The reactions couldn't keep up with the power that was coming in. And so what happened was you ended up having a big resistive effect, which produces higher temperatures. Ultimately, you could cause burning of the material, which then causes the device, which is sealed, to unseal. So gases are released and so forth. And you might say, well, how much power was put in to cause that effect? And I would say, as a mechanical engineer that who works on heat transfer, that it almost doesn't matter how much power was put in. Electrical engineers will always find a way to try to put more power into something or take more power out. The electrical engineer is always thinking of new ways to be more powerful. And so, you have to kind of expect that they will try to pull too much or put too much power into these devices. And, in this case, the supercapacitor did not respond fast enough to the power input. In this case, I want to also mention that if you could nanostructure your materials, nanostructuring gives you more surface area, it gives you shorter diffusion lengths, and generally speaking, it makes your device go faster. And I've had some conversations with people about these CV curves. So here's an example from the literature of a CV, a cyclic voltammogram, and what happens when you increase the rate too high, you start to see a change in shape of the curve. And I wanted to point this out to some of the students. You have the bird's beak type of curve for for 3 of the 4 samples. But then when in this case they went from 10 millivolts per second to 20, you actually start to shave off the beak of the bird, right? That's when you start to know that you're having some potentially irreversible reactions happening, or your system is just not fast enough to respond. Okay, when that happens, then instead of putting that energy into charge storage, the energy is going into a heating effect in general. Could be some irreversible chemical reaction as well. So I also mentioned earlier that supercapacitors tend to have a wider temperature range of operation, of safe operation. And this chart shows it. Here we're showing a number of different commercial technologies, supercapacitor technologies, and you see on the right side their safe operation temperature goes up to 70 in most cases, 70 degrees C, which so that I'll call that the Jodhpur regime of operation, right? And then also safe operation for most of them below minus 20 degrees C. So that's for me, that's like the Chicago regime of operation, where we can go nice and cold and things don't freeze up, right? Most of these supercapacitors use a organic electrolyte, and I'll talk a little bit more about the electrolytes here coming up. Even though that's a safe operating regime, temperature regime, it doesn't mean that your device behaves the same way, okay, within that range. So that's also important to understand. It might be safe to use it, but it will act somewhat differently. So here's an example. Over that temperature range I just mentioned, minus 40 degrees C to 70 degrees C, which again is a safe range, here's an electrochemical impedance plot, a Nyquist plot, where you can see that looking at this intercept, right? We would look first, I hope after yesterday's lecture, the first thing you'll look for is the intercept with the imaginary axis, because that's going to tell you something about the real resistance, right? So the series resistance in your device, and you can see that it changes by quite a bit. It changes by certainly a factor of 3 going across this temperature range. Although, for the higher temperatures from 25 to 70 degrees C, it's not all that different. It's relatively consistent. But when you get really cold, it moves down. All right, I'm going to talk about electrolytes and the effects that temperature has on electrolytes. And this is important. This chart is very, very complex. It has a lot of words. You'll have copies of the charts. You can read them later. The point of the chart is that it shows how temperature affects all these different aspects of an electrolyte, right? And if you just look at this, starting out with ionic conductivity and viscosity. So ionic conductivity has to do with these resistances that we have. So that would be in the solution resistance that we talked about yesterday. Viscosity can be important as well, because if my material becomes more viscous, it may have less propensity to penetrate into pores, into especially micro nanopores, and then I will have less surface area, and we all know that surface area produces higher capacitance. More surface area produces higher capacitance. Both of these, viscosity and ionic conductivity, are related to the diffusion coefficient through a couple of Einstein rules, and then temperature directly affects the diffusion coefficient, usually through mechanisms like hopping. We'll talk a little bit about that. And ultimately, these all combine to affect the capacitance and the series resistance of your device, which in turn influence your energy and power density. So this is all done through, really carried, these temperature effects are largely carried through the electrolyte. The effect of temperature on the electrolyte has a big effect overall on your device. I would note that proton transport in particular is highly temperature dependent. Protons, so ionized hydrogen atoms, hop around, or move around, I should say, through a number of different mechanisms. There's the hopping mechanism, where it's jumping from spot to spot in your system. There is diffusion, where you're getting more of a random walk and potentially some molecular diffusion along with the proton diffusion. And then monomer motion can actually also transport protons. So this would be monomer chains that are actually moving thermally and potentially electrostatically during the process. And as they move, they carry and portage the protons along. And we've mentioned the 3 types of electrolytes. I've made a spider chart here showing their relative attributes for temperature effects or thermal behavior for organic, aqueous, and ionic liquid devices, or electrolytes. You'll notice that the ionic liquids look good. They have a wonderful low temperature limit. They have a great high temperature limit, a high glass transition temperature for essentially for using them in low temperature environments. But they don't have very good conductivity. So their Achilles heel is a low conductivity, especially at low temperatures. You see the ionic conductivity, this blue point, that's the ionic liquid, is almost in the center of the chart at very low temperatures. So ionic liquids are high, their conductivity is highly temperature dependent. That's going to affect your series resistance, which will have an influence on overall performance. Aqueous electrolytes, on the other hand, look pretty good in this context, especially for conductivity, right? The problem is that they have a high low temperature limit. So it's just near freezing is going to be the low temperature limit. And that's not low enough for many applications, at least for general products, right? So I think that a supercapacitor whose electrolyte freezes at minus 10 degrees C is not such a big problem here in Jodhpur, but it's a big problem in Chicago. Okay, and that's why you have and companies want to make products that are generally applicable, and so that's a reason why that really hurts them in the marketplace. Kind of the compromise electrolyte between ionic liquids with their low conductivity but good temperature stability versus aqueous electrolytes with their very poor low temperature characteristics. Organic electrolytes kind of fill the gap in the middle. And they're a little bit better than these others for most of these characteristics. And so organic electrolytes, aside from relative cost to ionic liquids, which is advantageous for organics, are often used in commercial products. So now I'm going to talk a bit on overall performance, temperature effects on overall performance. We already touched on this this morning a bit.